All right, today we're diving deep into the secret architecture of pretty much everything solid around you. We're going to see how this hidden battle between atomic order and total chaos decides if something shatters or if it splits with perfect, clean precision.
So let's just start with a puzzle you've definitely seen before. You drop a glass, and it just explodes, right? Into a million sharp, curved, unpredictable pieces. But if you were to break a simple salt crystal, it would snap along these perfect straight lines. So what gives? Why are they so different?
It's a great question, and the answer isn't just, one is glass and one is salt. It goes so much deeper than that. It's all about the fundamental blueprint used to build the solid in the first place, one tiny atom at a time. To really get our heads around this, we have to look at the two basic playbooks that nature uses to build solid stuff. You can really think of it as this constant battle on the atomic level, a fight between perfect, beautiful order and complete, utter chaos. And this really shows you those two opposing strategies perfectly. On one side, you've got the architecture of order. All the atoms are lined up like little soldiers in a perfect, repeating grid. And on the other side, the architecture of chaos. It's just a jumbled mess of atoms, basically frozen right where they were. So these two atomic blueprints, they have names, of course. And they are the key to understanding everything else we're going to talk about, so let's get into the specifics and define what we mean by crystalline versus amorphous structures. Okay, first up, we have the champions of order, crystalline solids. In these materials, the atoms are locked into this highly organized 3D pattern we call a crystal lattice. And this isn't just a small, tidy little neighborhood of atoms. Scientists call this long-range order, which means that pattern just repeats itself perfectly over huge distances, at least on an atomic scale. A really great way to picture this is to just think about perfectly laid tiles on a floor. You see that repeating pattern, right? Now just imagine that same pattern stacking upwards and outwards, flawlessly, to build a whole structure in 3D. That one single tile that gets repeated over and over, in the world of materials, we call that the unit cell. It's the basic building block for the entire crystal. And this geometric perfection is exactly what we're talking about. The structure is so regular, so predictable, that, as this quote says, the exact same number of polygons meet at each vertex. It's this super strict repeating rule that creates those beautiful sharp-edged shapes we see in natural crystals, from a tiny grain of salt to a massive diamond. Now, let's completely flip the script and talk about amorphous solids. The name itself actually comes from the Greek for without form, which kind of says it all. There's no crystal lattice, no long-range order, nothing. But physicists have a much, much cooler name for them: supercooled liquids. That whole supercooled liquid idea gives you the perfect mental image. Just picture a glass of water, right? All the molecules are just tumbling around, a total chaotic mess. Now imagine if you could freeze it, like instantly, so fast that the atoms have zero time to get organized. You trap them in their messy, liquid-like arrangement. And boom, that's an amorphous solid. So we've got order versus chaos. Got it. But the big question is, so what? How does this atomic blueprint actually change how a material behaves out here in the real world? This is where it all gets really practical. You know, one of the easiest ways to see the huge difference between these two types of solids is to just ask a really simple question. What happens when you start to heat them up? And their behaviors could not be more different. A crystalline solid, think of an ice cube, it stays completely solid, right up until it hits one single exact temperature, its melting point, or TM. Then bam, the whole structure collapses and it all turns to liquid. An amorphous solid, like plastic or even butter, is totally different. It doesn't really have a sharp melting point. Instead, it just gets softer and gooier over a whole range of temperatures. We call that softening point the glass transition temperature, or TG. This table really pulls it all together. That internal structure just affects everything. Because of that ordered lattice, crystalline solids can actually have different properties depending on which direction you're looking at them. They're what we call anisotrophic. A great example is wood. It's easy to split with the grain, but super tough to break against it. Amorphous solids, on the other hand, are isotrophic. They're the same in every direction. And look, right there in that last row is the answer to our very first question. That ordered lattice creates these natural weak spots, these cleavage planes that let it break cleanly. The chaos in amorphous solids means there are no clean lines to follow, so when they break, they just shatter.
And this whole order versus chaos thing also controls how energy moves through a material. You can think of a perfect crystal lattice as being like a grid of superhighways. Energy, whether it's heat or electricity, can just zip through it quickly and efficiently. But in a random, amorphous structure, that energy just gets bounced around and scattered, which makes them much, much worse conductors. Look, this isn't just theory for a science class. These two atomic blueprints are literally the foundation for nearly every solid material we use. So let's take a look at how we've actually managed to harness both order and chaos to build our entire modern world. The power of chaos is actually incredibly useful. The whole reason glass is transparent and can be molded into basically any shape is because of its messy, amorphous structure. And the flexibility of the plastics in your phone case, or the elasticity of the rubber in your car's tires, yep, all of that is possible thanks to that random jumble of atoms. But when we need the absolute best performance, when we need incredible strength, durability, and total predictability, that's when we turn to the power of order. I mean, the entire digital age runs on the perfectly crystalline structure of silicon wafers, the amazing strength of the metals in our buildings and cars, and the unmatched hardness of things like ceramics and diamonds. All of that comes from a flawless, repeating atomic lattice. So, from a shattered cup to a perfect diamond, the real identity of any solid really just comes down to its secret architecture, that fundamental choice between chaos and order. Think about it. Our modern world was built by mastering crystalline silicon for our computers and amorphous glass for our screens. It really makes you wonder, what new materials and what new atomic blueprints will define the world of tomorrow?